Uh, Professor K. Siddhappa, former Vice Chancellor of Bangalore University, is with us. I welcome him, and he is going to be here for the PC Deshmukh's lecture. Thank you, sir. Okay, sir, you can go.
No, I'll give another microphone.
Good afternoon. A very warm welcome to all the dignitaries, delegates, and student representatives, and my dear volunteer students. So, today it is indeed a great pleasure to have our distinguished speaker, Professor PC Deshmukh, who is a mentor and convener of Center for Atomic, Molecular and Optical Sciences and Technologies at IIT Tirupati and IISER Tirupati unit. He has been a professor, he is professor of physics and dean in IIT Tirupati. He has also been associated with IIT Madras and IIT Mandi, and he has over 350 research publications, of which 150 are been published in peer-reviewed journals, and nearly he has presented over 200 conference proceedings. And to be more delighted, nowadays we are aware of this Swayam platforms, which has been part of NEP program. And Professor PC Deshmukh has been very active, and he has nearly given 4 full courses on NPTEL, as well as he has also over 178 video lectures, which is available on NPTEL, NKN and DTH libraries. Apart from this, Professor Deshmukh has also published books on quantum collisions and confinement of atomic, molecular species and photons, as well as foundations of classical mechanics. And very shortly, we will be expecting a book on quantum mechanics as well as atomic physics from Professor Deshmukh. Apart from that, sir has also been an editorial board member for Institute of Physics journals, Physica Scripta, as well as he has been chief editor for 4 conference proceedings: Pramana, Journal of Physics Conference Series, Springer Proceedings on Quantum Collisions and Confinement of Atomic and Molecular Species and Photons 2019, Physica Scripta 2022. Sir, it is really it's a great pleasure to have you in this institution. And sir has, if we look at the number of students whom he has guided, it is nearly 17 students he has guided for PhD. And one student, Dr. Shanti, she is also available, she is also part of this program. Madam, we welcome you, as well as she is distinguished professor at Department of Postgraduate Studies in Physics at Jain University. Sir, your student is also part of our NSSP program, and shortly Professor Deshmukh will be delivering a talk on teleportation and quantum computation physics, Nobel Prize 2022. So over to you, sir. Thank you, sir.
Thank you very much. Greetings and good afternoon, everybody. It is wonderful to be here on this occasion. This is such a wonderful gathering, and very inspired by Professor Uday Shankar's talk this morning, followed by Professor Ahluwalia's as well. And this is a great start. So let me begin the talk by talking about the uncertainties in life. Life is full of uncertainties, and that's what makes it really exciting. Means we know that, okay, when you toss a coin or when you gamble, you don't know if you will get 3 or 4 or 6 or whatever. and you can win or lose games and kingdoms, and sometimes even your wife, as we know from Mahabharata. So these uncertainties are an integral part of life, and what we are going to talk about today is what is behind this uncertainty, and we will try to appreciate what is it that led to the Nobel Prize to these stalwarts. I am sure you have seen their pictures, you know their names, and you know what the Nobel Prize is about. So we will get to that. So the Dharmakshetra and Kurukshetra is with us again. So is the teacher and the student. Krishna, the teacher, Arjun, the student, confused Arjuna in total vishad, as we refer to this, not knowing what to do. And Arjun knew that, okay, Krishna is the God, he is the Lord, and he would do whatever he would tell. But Krishna's insistence was that you must understand this first. And if you understand it, then you take your own decision. And you need to understand this. So here, the choice is between, do I fight or do I not fight? Yes or no, black or white, 0 or 1, the switch on or off. These are the choices that we always have to make. It could be there in a cricket match. Okay, do you call heads or tails? If you win the toss, do you bat or do you bowl? Hamlet had the same question. And this choice of 1 or 0 was developed as a whole mathematical scheme which we call as symbolic logic, which was developed by George Boole. And then you are familiar with the truth tables. And they became the basis of computing, because Shannon realized that you can translate the Boolean algebra into electrical circuits and you can actually do computing. So computing as a tool to answer questions of, do I do this or that? And most of your logic will boil down to if then else kind of logic. And you build your algorithms based on this logic, based on Boolean algebra, which is a binary system of a switch being either on or off. So now what happens in nature is different. And it is not correct to say that quantum mechanics is strange. It's not quantum mechanics that is strange. It is nature which is strange. Quantum mechanics describes it correctly. And classical physics, in fact, does not describe it correctly, which actually makes classical physics strange and not quantum mechanics. So that is a point that I would like to begin with, that it's not quantum mechanics that is strange, it is nature which is strange, and you are trying to describe the laws of nature, which is the job of a scientist, which is to understand how nature functions and how do we interpret whatever happens in nature. And the way things happen in nature are different. It is not just a choice of this or that, 1 or 0, but you are confronted with superpositions of 0 and 1, a superposition of a possibility of a cat being dead or alive. Now this is a superposition which is how nature manifests herself, and our job is to interpret this. Now this is what brings us to quantum physics, and Feynman pointed out in the early 80s, although he was not the only one to do so, there were a couple of others also who had the same idea, they were working on the same idea. Benioff was there, Deutsch was there, but Feynman's remark is very well known. He was giving a keynote address at MIT, and he said that if you are to be building computing machines, then it is best that it is done using how nature functions, and nature does not recognize 0 and 1 separately when both are accessible. When only one is accessible, it is a different story, but when both are accessible, nature chooses a superposition of the two. So, let us talk about these two possibilities. So, there is a bed of sand here, and there are two openings over here from which sand can fall, and what you expect are these two heaps. Now, this is what we expect. Now, this experiment, which was done by Thomas Young, was a polymath and somebody who knew just about everything, and Young did these experiments, and he found that when you have light falling through two slits, you actually get interference, and I am sure that all of you are familiar with this experiment, and most of you would have done this experiment. And this is a stunning experiment, that instead of getting two heaps, you get patterns of dark fringes and bright fringes, and this is a very shocking kind of result, and you need to understand why this is important. And this experiment, if you Google 10 most beautiful experiments in physics, you will find this listed. But the other thing which is of importance over here is that, as Feynman mentions in one of his lectures, almost everything that is there to be understood in quantum mechanics is there in the interpretation of the Young's double slit experiment, which is why I really urge you to pay attention to this. So, here is this double slit experiment, and let us do this experiment now. This experiment can be done with photons, you can do this experiment with electrons. As a matter of fact, when Feynman talked about it in the early 60s, this experiment was not done. It was done almost 30 years later in Japan, but we will discuss the consequences of this experiment, and you can do this experiment with either electron gun or photons, or it does not matter. So, what happens, the particles have got two trajectories accessible to them, and whenever there are alternatives which are accessible, nature can be interpreted only as a superposition of both, not just one or the other, and that is what gives rise to this interference. So, you are interested in finding out that, okay, if the particle would have entered the apparatus either through slit 1 or slit 2, let me spy on it, let me do some other experiment, and let me figure out from which slit the particle has actually entered. Now, this is called as a which way experiment, and when you do this which way experiment, you will have these two rays, either you will be able to figure out that it came out of either slit 1 or slit 2, and then you can say that yes, now I have found out from which slit the particle has entered. But if you do a which way experiment, the interference fringes that you had seen, bright and dark fringes, this interference disappears when you do a which way experiment. Now, what is interesting is that you can put a lens here. Okay, if you put a lens here to combine these two rays and bring them to a focus, whatever information you got from the which way experiment is lost, because what has happened is that the two rays are brought together, and now you do not know anymore from which slit the particle has come, and the information that you got from the which way experiment is destroyed. So, this is the quantum eraser, and what the quantum eraser does is it restores the interference. Now, just by doing something over here, the pattern over here changes, which is really mind boggling, and this is something that classical physics cannot interpret. By doing something over here, you just insert an additional apparatus over here, you lose some information and the interference is restored. And what is even spookier, this is a term which Einstein used, that quantum mechanics requires you to come to it, you are confronted with spooky kind of phenomena. And what makes it even spookier is that if you move this lens, if you move it to the left and over here and over here and over here, can you see the spot, the laser spot? And you move it away and put it somewhere here. You can take it away and put it like 10 kilometers away, or even thousands of kilometers away. And the lens is no longer in the region of what you believe is the apparatus. So you have a certain perception of reality, some perception of a physical, local determination of what is where. And these are the terms which are going to be challenged when we interpret this experiment. Because what happens is that if you move this lens away, this is called as a delayed choice which way experiment. It's delayed choice because the time light would take or any particle would take to reach that lens, which is moved away, far away, hundreds of kilometers away from this, it will still have the same effect the moment there is a lens which has the capacity to combine the rays. The interference pattern is restored. So this is mind-boggling, absolutely. How do you interpret this? So this was an idea which John Wheeler came up with, and let us look at some more possibilities. And now we are going to think about even more possibilities. So here is again a Young's double slit experiment. There are two slits over here, but there is another shutter over here, and you have these alternative paths. But let us think about even more different paths. So let us think about these paths. There is a scatterer here, there is a obstacle over here, and this can be anywhere in the universe. It can be on Mars or Andromeda galaxy or anywhere, it doesn't matter. But you can think about all these alternative paths. And the way nature manifests herself makes it necessary for you to include in your analysis all of these paths. This is called a sum over histories. And quantum mechanics was formulated, as I am sure you know, by Heisenberg, Born and Jordan, but it was also formulated by de Broglie, Schrödinger and so on. There were other formulations. As a matter of fact, there were like 9 equivalent formulations of quantum mechanics. The fundamental theory is deeper, and all of these wave particle dualism, matrix mechanics and so on, these are different expressions of a fundamental theory which is quantum mechanics. So when you look at all of these possibilities, I am referring to one of the formulations of quantum mechanics which was done by Richard Feynman, and almost 20 years later, after the quantum mechanics that was developed by de Broglie, Schrödinger and Heisenberg, in the late 40s, Feynman developed with this methodology which is called as the path integral method of quantum mechanics. And in this you must combine all of these paths, and now you can ask, what would be the momentum of the particle if the particle has to go to if the particle has to go to Andromeda and come back into the apparatus? What kind of speed would it require? This galaxy is 25 million light years away. How long would it take? Means light itself would take 25 million years. So why do you have to consider these possibilities? But then can you even talk about momentum? If you are talking about the trajectory, if you are talking about a path, you know the position, and you have lost information about momentum altogether, because it is impossible to get simultaneous information about position and momentum, and that is something which you understand using this 1.22 business that we talked about earlier, that if you talk about the resolution of a microscope, and the microscope that you have in front of you is known as the Heisenberg microscope, and I will not go through the analysis in details, but if you want to look at a particle, there is an electron over here, you want to see it, so you look at it from this eyepiece, and with what accuracy can you get this information? You can get information about its position only by shining light on it so that you can see it at all, but when you shine light on it, you cannot avoid the momentum transfer between the light and the particle, and that makes it impossible. And then one can do some analysis. The Heisenberg microscope does not give you this relation exactly, it gives you an order of magnitude relation which is correct. This relationship is much more rigorous, so I will not go into the derivation of this, and these quantities are defined in terms of a minimum uncertainty that you cannot avoid. So, you cannot get information about position and momentum, and that means that you do not have to worry about what should have been the speed of the particle if it had to go to Andromeda and back. Why are you even asking about the momentum if you know the position? So, physics does not answer all the questions, it tells you what are the right questions to be asked, and this is what Niels Bohr explained, that how to do physics, you have to ask the right questions, and then physics will tell you how those are understood. And then this brings us to the question of uncertainty, the gambling, the toss of a coin. All of these involve uncertainties. They involve probabilities, and the probability is understood only in terms of this coefficient here, that if position and momentum cannot be known simultaneously, then you cannot describe the state of a system by a point in the phase space, and then you need a different machinery. Either you quit physics or you invent a new methodology, and the new methodology is quantum mechanics, that you cannot represent a system by a point in the phase space, so represent it by a vector in the vector space. Now, all this seems to be abstract, but you will see that it becomes very real. In fact, it becomes more real than classical physics. The reason it becomes very real, because when you describe a system by a vector in the vector space, which you can expand as a linear superposition, and this is the two slits. There are two possibilities, and both must be combined with appropriate coefficients, and the probability is the only thing that you can measure, and that is given by this amplitude square of this coefficient. So, now here is another thing. So, means you can understand, means you are already recognizing that this is mind boggling, but Einstein was very troubled by this, and you can see the origins of this trouble from this interferometer experiment. So, here is something similar to what I described as in the previous Young's double slit experiment. This is called as a MacZinder interferometer, and just by obstructing this path, so you see the interference pattern at the detector, but if you obstruct one of the paths, you can change the interference pattern, and you can explain it only if you go back to this relation, and this becomes your fundamental source of interpreting probability, which you will recognize to be different from how we recognize probability in classical physics. So, here if you just stop this, you have this obstruction over here, and you can change what you see at the detector, and you can understand this only in terms of probability. Now, this is shocking, because one very interesting experiment which was proposed by Elitzur and Weidman in 1993 is this bomb tester, and I would like to mention it because you will appreciate what a stunning understanding of probability quantum mechanics gives you. So, this experiment is the following, that you have got a bomb over here, you do not know if it is live or it is one of those Deepavali bombs which do not blow up. Okay, there are some of those kind, right? And that a bomb which you expect to be deployed, somehow because of some deficiency doesn't work. That is called as a dud. So there is a live bomb and there is a dud bomb, and there are a bunch of them, and you are told that, okay, I want you to use the bombs, and you have to bring me only those which are the live bombs, because if you bring the dud bombs, they will be of no use. So what do you do? How do you know whether a bomb is a live bomb or a dud bomb? And the bomb is designed in such a way that there is a sensor here, and if light passes through this, then the bomb is going to blow up. So if it doesn't blow up, then it is a dud bomb. So there is a mechanism which is built into the bomb. So are you going to use this mechanism? Because if you use it and the light goes through it, okay, and you find that it is a dud bomb, then the bomb is no use to you because it is a dud. If it blows up, it is not available to you anymore. So you have to be able to use this mechanism without risking the bomb to blow up. Can you do that? And the answer is actually yes, which is really very remarkable. And the way to do it is to use this MacZinder Interferometer, and this is a thought experiment which was proposed by these two Israeli physicists, which is a very fascinating experiment. And the way it works, I mean, it's not going to work every time you try it, but there is a 50% chance that you will be able to detect which is a live bomb without having to burst it. It's not guaranteed, but there is a chance that you will succeed, and that chance is actually 50%, not bad. And you can improvise on the technique and raise the probability of detection. You can almost bring it to 99% using more sophistication of this MacZinder interferometer. So using this, you can actually figure out. Now all this works for one simple reason, that probabilities are defined by the modulus square of the coefficient. So that's the fundamental thing. And Einstein found this to be, means everybody is concerned about this, that okay, there is probability, I don't mind, probabilities have been there right from the time of Mahabharata or even earlier. So people have been gambling and working with uncertainties. So, but what is the origin of this probability? So let us ask that question. So this question was debated hotly. Most, the Einstein-Bohr debates are very well known, and this is the picture which everybody has seen, 1927. Look at the intellectual density in this picture, it's amazing. All of you should have a personal copy of this picture. Almost everybody who contributed to the development of physics is in this picture. And the debate between Einstein and Bohr continued because Einstein thought that there is something missing in quantum mechanics, which is why you have this probability. And it was natural to expect this, and Einstein was very correct in suspecting that there is something missing in this, and that you can see in all of these pictures. Think about the toss of a coin, and you cannot predict whether it will fall on heads or tail, and that is where the probability and the uncertainty is coming from. But why should there be any uncertainty? If you toss a coin and if you knew exactly where you are applying the force, okay, you are doing it like this, right? You know exactly where you are applying the force, how much torque is applied, how much it will spin. If you know the density of air, the humidity and other parameters, you can calculate how many times it will flip, and you can actually predict that it will fall on heads or tail. There has to be no uncertainty if laws of physics are deterministic. The only uncertainty that is coming is because you do not know at this point how much torque was applied and what are the other forces of air which are acting on the coin. So, this information is not known. These are the hidden variables. So, the uncertainty is coming not because the laws of physics involve any uncertainty, but because there is some information which is hidden from you. If you could plug in this information, the calculation may be difficult, but one can hope that there will be no unpredictability and everything will be certain and deterministic. So, Einstein's view was, yes, the probabilities which are talked about in quantum mechanics, there is nothing wrong with it, but what is missing in quantum mechanics is information about the hidden variables, and if these hidden variables are recognized in a later theory which would supersede quantum theory, then causality and determinism would return to physics. So, this was Einstein's point of view, which was a very powerful point of view, and Einstein came up with a large number of thought experiments to explain this, and these were countered by Bohr, but it was only a debate between 2 points of view, Einstein on one side and Bohr on the other, and both had plausibility associated with it, but it was impossible to know which argument was actually correct. And Bohr definitely defeated Einstein's arguments every time by finding a fallacy in Einstein's argument, but he could not come up with a method to demonstrate that the thinking was intrinsically not correct. And it took quite some time. In fact, it took almost 30 years for this to happen, and Einstein summarized this in his paper in 1935, which is known as the EPR paradox, after Einstein, Podolsky and Rosen. And the paradox is the following, that if you have an explosion over here and two particles move away from each other, one toward the east and the other toward the west. So, Einstein argued that, okay, I cannot measure position and momentum of the two together, but let me measure the position of this particle and I will measure the momentum of this particle. And then from symmetry and conservation laws, I can get simultaneous information about position and momentum both. So, this was his counter to the Heisenberg microscope, to the uncertainty principle. And this is paradox because on one side you are accepting the uncertainty principle that position and momentum cannot be known simultaneously, but here you can get around it by figuring out using position and momentum and conservation principles. So, what the information that you are really using is something that you have not measured. You have position of this and momentum of this, but you have not measured the momentum of this. It is like talking about something without carrying out an experiment, and I think from the beginning of this morning through Professor Uday Shankar's talk and Professor Ahluwalia's talk, the reference to Raman's work, one theme that is running in every talk is the idea of doing experiments. This is fundamental. Can you talk about something that you have not measured? And Einstein asked this question in a very dramatic way. Is the moon there if you are not looking at it? Now, the question seems very simple, but the answer to this is very complex, because you can only talk about what you are measuring. And if you are talking about the position of this and the momentum of this, can you infer properties of this even if you have not measured? So, this amounts to a formalism which involves what is called as counterfactual definiteness, that there are these properties which a system has, and you can talk about these properties even if you have not obtained information about it, even if you have not carried out measurements to understand to know what those properties are. And this is Einstein's definition of reality. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. That without disturbing the blue particle, if you say that I can figure out what its momentum is, then you attribute a certain reality to that property. And this is our interpretation of reality. This is the common interpretation of reality. This is the interpretation that Einstein assigned to reality. But we will see that quantum mechanics requires you to sort of upgrade this perception. So, this is the counterfactual definiteness. So, let me give you some examples of this counterfactual definiteness. This was countered by Bohr in the same year in another paper with the same title. But Einstein's conclusion was that there must be hidden variables which will restore causality, whereas Bohr's conclusion was different. But then it took like 30 years. In 1964, John Bell came up with a method, and John Bell said that okay, this debate will not take you anywhere. As a matter of fact, there is a story that John Bell and Bohr were together at CERN, and they were riding an elevator together, and Bell was almost he was very upset with the way Bohr had argued this, because he said that okay, these arguments will not take you anywhere. There has to be a method of figuring out whether counterfactual definiteness has got any value. So, here we go back to this toss, and Bell came up with this method, that yes, there is uncertainty, but this uncertainty can be removed by hidden variables. If you can get exactly how much torque was applied, what is the density and humidity of air, what are the forces acting on the coin, you can actually predict whether it will fall on head or tail, and there is no uncertainty, because Newton's laws are completely deterministic. From initial conditions, you can get a solution at a later time as well as at an earlier time. These are symmetric under time reversal. So, Bell said that the way to figuring out, to solving this puzzle, is to look at correlations between different games. So, here are two other games in play in operation, and there are three captains. I think Rohit Sharma is now struggling to find his place in the team, but in every case there is a possibility that the coin will fall on a head or a tail. And the kind of question you can ask, what is the correlation that Rohit Sharma will also get heads when Dhoni also gets head? What is the correlation between Smriti Mandhana getting a heads when Rohit Sharma gets tails? So, these are the correlations that you can examine if these correlations are governed by hidden variables. So, let us look at these three possibilities. There are three games in our consideration. One is in the red frame, the other in the green, and the third in the blue. So, I am going to carry these three colors, red, green and blue, in the next slide. So here we have the red, green and the blue, and I have 3 circles in those colors, okay? And each circle either overlaps with the other or it doesn't overlap. So it is like heads or tail, 1 or 0, a switch being on or off, okay? So that keep that Boolean logic at the back of your mind. So red may overlap with green or it may not, but red may also overlap with blue or it may not. So now let us look at these segments. There are 7 segments, and now we play a game. We play the game which is pin the nose. Now you know the game pin the nose. So here is a cartoon over here, and you would have played it when you were children, or maybe you play it with your children or with your younger family members. And there is a cartoon over here, and you are blindfolded, you are given a pen, and you have to go up to this figure blindfolded, and without looking here, put your pen here. Now if you are not looking at it, you put it here, or maybe here, or maybe here. Your task is to pin the nose, put it right over here, and if you do it, you win the game. So now what you are going to do is to play this game on these 7 segments. There are these 7 segments, and you are playing pin the nose, and there is a certain probability that you will pin the portion in the segment 7. There is a probability that you will pin the segment 5, and so on. All of these are probabilities. Nothing is certain. But if you just look at the area, you will easily see that the probability of green not blue plus blue not red is greater than or equal to green not red. And this is very easy to see, because you have the pictures, and mind you, there is a hidden variable here, because the green not blue tells you nothing about the red. It is a property that you have not measured. Okay, go back to the EPR paradox, that can you get information about a property which you have not even measured. Okay. So here you are getting around it, and whenever you have hidden variables, you have this type of inequality. This is the Bell's inequality. The Bell's inequality applies to all those situations where uncertainties and correlations are governed by hidden variables. So here is an example of a hidden variable which is involved, and as a result of this you expect this inequality, because green not blue includes green not blue overlapping with red and green not blue not overlapping with red. Okay, so those are the possibilities which are both included. Those are the hidden variables, and whenever you have hidden variables which explain the correlations, you are led to an interpretation which involves local reality, and the probabilities are then governed by this inequality, and you expect this inequality to be satisfied. So Bell said that, okay, if you think that quantum mechanics has got probabilities, uncertainties, and as Einstein argued, it is because of hidden variables, then such an inequality must be satisfied. Bell's inequality must be satisfied, and that is a way to figure out whether Einstein's argument was correct or Bohr's response to it was correct. So now there is a method, and you can actually carry out a measurement. You can carry out experiments, and experiments in quantum mechanics are governed by probabilities which are determined by the modulus square of the coefficient, which is what I talked about, and nothing else. So quantum mechanics is different, And now you can do an experiment and you can have a singlet state which fragments into two spin half particles and they go in opposite directions, and you have exactly the same question. Again, I have a red, green and blue in this picture. There are three captains who are doing a toss with two possibilities each. Alice measures spin up and Bob measures spin down. These are the two possibilities, and you do this experiment, and you can do this. The three colors correspond to the fact that after all, when you do this Zeeman effect or the Zeeman spectroscopy, you are carrying out measurements in a basis set, and the basis set is something that you align along with the magnetic field, the z axis. But the z axis can be like this, or it can be like this, or it can be like this, whichever way. And Alice and Bob are carrying out these measurements. Alice doesn't know what basis Bob has chosen. Bob doesn't know what basis Alice has chosen, and then they compile the results. Did you find spin up or spin down, and so on. These are the two possibilities for a spin half particle. And when you combine all of these things and then you look at the correlations just the way you did with the correlations in the overlap of the three circles or in the toss of the three captains, and those were determined by either 0 or 1, and these are also determined by either up or down. There are two possibilities. It's exactly the same problem, same colors. The difference is, if these correlations are governed by the local hidden variables, then you expect the correlations to be in accordance with the Bell's inequality. Okay, because that is a kind of inequality that is satisfied when you have local hidden variables. But then here the quantum probabilities are determined by this equation, and they are not determined by hidden variables. So Bell's inequalities are violated, and which is why John Bell's work is considered to be so important, because he proposed a method so that you can actually carry out experiments and figure out whether the probabilities in quantum mechanics are governed by hidden variables, or is it a different way of describing nature, which is what we call as quantum mechanics. So Bell's inequality must be satisfied by all theories that are both local and counterfactual. And then it turns out that when you carry out these experiments, and these are the experiments of the 3 Nobel laureates of 2022. They did these experiments, and what they confirmed is that you do have correlations which, however, violate Bell's inequality, which means that quantum theory is either non-counterfactual or non-local. Non-local means it has got serious implications on our perception of reality, because we do not interpret reality in this sense. So, which is why this has been described as the most profound discovery of science by Henry Stapp. So, it means in fact it is given importance even more than the original formulation of quantum mechanics, because it tells you how to resolve a very subtle issue. There were two intellectual giants involved in this debate, but they were not the only two. Means let me also mention that many others were involved in this, and these experiments were carried out. John Clauser carried out these experiments. In fact, he collaborated with a student, Friedman, which is again a nice thing to be mentioned in a student-teacher symposium, because this is the collaboration between a student and a teacher. And Friedman was not directly Clauser's student, but he carried out these experiments. There were some sort of loopholes in this, because it could be argued that the correlations could be accounted for by a hidden variable theory, and then these loopholes had to be plugged in, and that was the work of the other two Nobel laureates, and it opens up a different world for us, because now we must interpret reality in a different sense. And Feynman's suggestion that if computing is to be done, then it is best that it is done according to how nature functions, and nature does not exclude two alternatives whenever both are accessible. You must consider a superposition of them. So, you can't be using Boolean algebra anymore. You can't be using those classical gates, the AND gate, the NAND gate, the OR gate, the exclusive OR gate, and everything that you have learned. So, those are not the gates which are going to provide you with the most efficient computing formalism. You should use quantum computers, because quantum computers work not with these classical bits 0 or 1, but they work with a superposition of 0 and 1, and this superposition is like the superposition of a cat being dead or alive. Now, mind you, these are distinguishable qubits. So, elementary particles are indistinguishable. They are either Fermi particles or Bose particles, but qubits, we are having two qubits, one with Alice, the other with Bob. I call them as Aditi and Bharat. So, there are two qubits, one with Aditi and the second with Bharat, and when you do mathematics, not with the binary Boolean algebra, but with the algebra that quantum mechanics asks you to use. So, you must now develop gates, not the AND gate and the NAND gate and so on, but you need quantum gates, and these quantum gates are very well developed and understood. Deutsch was one of the first ones to use it. I like to mention Love Kumar Grover always, because he was like one of you, and look at how alert he was, because he I believe he passed from IIT Delhi around around the same time that Feynman gave his lecture, and about 10-15 years later he came up with the Grover algorithm, the search algorithm, which was one of the first ones to be developed using qubits. And this was in an era when there were no computers, there was no computers in the sense not internet, accessibility to information, Google's type of search engines, nothing was there. And he obviously researched all of this, stayed up, and was one of the first ones to contribute to a quantum algorithm. And it opens up completely new technologies, because now you have a superposition of 0 and 1, and you can this qubit, this is a qubit which is with Alice. She does not know what is the value of the coefficient A0 and A1, because the only way she can get this information is by doing an experiment, but the moment she does that experiment, the system collapses into an eigenstate and it does not remain in the superposition anymore. So, she has to be able to convey this information to Bob, who is at a remote location, and this is what brings us to teleportation. Teleportation is Alice communicating this information about this qubit, which is a quantum superposition of 2 bits, to Bob, who is remote, and is she able to do that? So, they do have some additional resources. The additional resources that they have 2 other qubits which are entangled, and they are entangled means that their state in the vector space cannot be written as a product of factor states. Okay, so, they are not factorable, and such states are called as entangled states, or they are also called as Bell states. Okay. So, the resource that Alice and Bob have is 2 qubits in a Bell state, and what Alice can do is entangle the first qubit. This is the information that she wants to communicate to Bob, and she can entangle this qubit with this, but because this one is entangled with this, the information can be passed on to Bob, without her knowing what is A0 and what is A1. Now this is amazing because it doesn't matter. Have we referred to the distance between the two? Bob can be in the next lab. He can be in a different town. He can be in a different galaxy. It doesn't matter. But Bob is able to get that information because of this entanglement. And people sometimes wonder, are we violating the limits that we recognize from the special theory of relativity? So special theory of relativity is talking about speeds. And what is speed? Means speed, right now your speed is 0 relative to me, but if I start moving in any which direction, your speed changes. And you have a certain speed. Speed is something which can be understood only relative to the observer. But the speed of light is the same for all the observers in an inertial frame of reference. Any observer in an inertial frame of reference, and that is the limit that no physical object can be accelerated past this limit. So if regardless of how far Bob is, even if he is in the next room, light takes a finite amount of time to get there, whereas this is happening instantly. So it is not something which travels at all. There is no travel involved. What is travel? You traveled, somebody traveled from Jaipur to Bangalore. You started at a certain instant of time and arrived at a certain instant of time. Travel takes place between 2 points over a time interval. But here your idea of 2 points is destroyed, because what is challenged is your understanding of locality. What we learn from Bell's inequality is that you have to arrive at a new interpretation of locality, and this reality that you get from quantum mechanics. So there are like two persons, they are at different locations, but there is some bond. It has nothing to do with where they are. This is Dushyanta and Shakuntala. It's a painting by Raja Ravi Verma. And the location is of no relevance at all in this, because this phenomenon is completely governed by entanglement, and there is nothing like here and there. The difference between here and there is destroyed. So no question about anything traveling from here to there. What is here and what is there is, this is my last slide. Yeah, this is almost my last slide, I think. So there is no difference between here and there. Reality itself is non-local and it is very spooky, but there is no travel. So the question of challenging the speed of light or anything is irrelevant, and this is what I call as reality 2.0. And the experiments of Aspect, Clauser and Zellinger established this conclusively, which is the Nobel Prize that we are celebrating here. So thank you very much. I'll be happy to take questions.
Then professors will have many questions to ask, but first preference for the students. One student.
Sir, a few days back we had one more professor, Arvinda S. from IIT Tirupati itself, and he also enlightened us with about this Nobel Prize. So my question is there a limit to quantum computation or quantum mechanics after which we will not be able to realize the nature, or nature is really it is not linear, it's non-linear, or we can't really interpret nature. So will there be a limit to quantum mechanics, and we'll have to go for a new paradigm? What would you like to say about this?
I'm not sure I understand your question, but let me respond to it the way I have understood it. Please sit down. I will refer you to a recent paper by Lee and Selby, and they've come up with a mechanism to address this question. We have arrived at quantum theory not as our first theory of nature. Prior to that, we went through several theories, and Newton asked this question as to the position of a planet is here today, what will it be tomorrow, what will it be day after tomorrow. So these are the questions which interested in Newton when he was about your age, he was 21. And he had to ask what is the rate at which the angle theta is changing with time. So what is delta theta by delta t in the limit delta t going to 0? And he asked this question when there was no calculus. So he invented calculus at your age. And he developed a theory which gave very good results until experiments required you to go beyond it. And what we now understand means, because I pointed out that if you cannot get position and momentum at the same time, you cannot solve Newton's equations. So it is classical physics which is strange, that it seems to work when it shouldn't. And the reason it works is because it is an excellent approximation to quantum mechanics, and an approximation which works in a large number of situations within its limitations, but it works. So now your question amounts to asking, is there a theory which will supersede quantum mechanics, to which quantum mechanics will be a good approximation? And we know from what we just discussed about classical physics that it works because it is a good approximation. All those paths through Mars and Jupiter and everywhere, those must be taken into account, but they add up out of phase and cancel each other. So classical physics works because it is a good approximation. When action is small, it doesn't work.
Okay.
So Lee and Selby have an answer to your question.
Okay, sir.
The answer to your question comes from Lee and Selby's work. They asked this question, can there be a theory which supersedes quantum mechanics, to which quantum mechanics is a good approximation? And you are asking if one can go beyond quantum mechanics.
Yes.
So this is a no-go theorem. You know what a no-go theorem is. No-go theorem is, it tells you something that can happen or cannot happen. Okay? Can you trap an ion with electrostatic fields? Okay? Earnshaw's theorem, that is also a no-go theorem. Okay? No cloning theorem, for example. These are all no-go theorems. So they have a no-go theorem that there cannot be a theory to which quantum mechanics is an approximation. So the answer is no. However, Lee and Selby also pointed out that there are certain assumptions they have made in their model, and subject to those assumptions, this is their conclusion.
Okay, sir. Thank you,
Does it answer your question?
Yes, sir. I'll
Okay.
look into the paper.
Okay.
Any other student? Yes? Okay. Yeah, quickly you ask the question because time is up.
Sir, so the question about the Bell inequality was there was something on the free will was also dependent on the answers of that inequality question. So the new Nobel Prize and the results we have got, or the things we have understood, what implications it will have on the self-determinism and free will?
Well, these terms one has to use very carefully, and they have a very subtle interpretation in its own context, and I don't think I want to venture into commenting on it unless we have the time and sufficient opportunity to discuss all aspects of it, because it's a very treacherous domain. So I don't want to get into that.
Professor Kokila has one question. I think.
Yeah. I have a question about something which you explicitly did not discuss. That is, when we write down the wave function of two entangled photons or electrons, we just consider only the spin part of it. Spin part of it. But what happens to the spatial part? Definitely one must have a spatial part, and we must show in a consistent theory that the spatial part vanishes or does not matter at all. And especially in quantum mechanics, we don't have the wave functions in a system where a particle decays into two particles like that. In the case of, so can you comment on that?
Yeah, sure. That is not a limiting factor in the interpretation of the experiments at all, because certainly the complete wave functions, of which spin is an integral part, the interactions, what is interacting with the magnetic field is the spin part of the.
I understand, but nobody mentions, not even mentions that there is a spatial part and that has to be considered, and that vanishes, does not make sense. It is not useful in this particular context.
Yeah,
that's what I'm bothered about.
No. It is very much there, but it is not interacting with the application of the magnetic fields. What interacts with the magnetic field is the spin part, and that is the interaction which determines whether the measurement results in a spin up or a spin down. So I don't think anybody ignores the fact that there is a spatial part, except that it is not involved in the interactions under consideration.
Okay, sir. Okay. Yes, sir. Professor Deshankar has something to say.
Yes.
I want to say that you brought in Young's double slit experiment. All the modern day radio telescopes work on the principle of Young's double slit experiment. No matter whether it is GMRT with TFR is built or the one that you see in the movie Contact, you name them, all the modern telescopes use Young's double slit experiment as the basis of their imaging. Thank you.
Yes, sir.
Yeah, thank you very much.
Oh, yes, sir. Thank you very much, sir, for your talk on that, especially. I think the students must have enjoyed your talk. And I request Professor Shivramyan Patil to...
Sir,
one more information. Sir, can I share your email ID to these students so that they can interact? And moreover, during lunchtime, you can actually talk. Yes, sir, I will. After.
Sir, I have
Question,
one
sir?
question here. Yeah.
Sir, ಆಮೇಲೆ ನೀವು ಒಂದು 10 ನಿಮಿಷ. Okay.
Something relevant to students.
ಮಾತಾಡ್ತೀರಾ ಅಂತ.
Not at all. Here only.
Sir, one question here about the local and non-counterfactual part of it, non-local and non-counterfactual. So understood the non-local part, I'm trying to understand the non-counterfactual part of it. If you can explain briefly about that, that would be.
Well, non-counterfactual means that non-local hidden variables are not ruled out by these experiments.
Okay.
Local hidden variables which are involved in the toss of a coin, those are ruled out. But is there any non-local hidden variable which is involved in your interpretation of reality? Okay. That possibility is not completely ruled out.
So what do we mean by non-local hidden variable?
So any example means, I know that might be something abstract, but can we give...
There is no classical analog to this.
Okay.
Okay. The only thing that can explain this is quantum mechanics,
Okay.
which is entanglement. So an example of non-local hidden variable manifesting itself is through entanglement.
Okay.
And entanglement is real. That is how quantum computers work. That is what will give your money security in your bank account. It works. And I always like to point out that nothing succeeds like success. So quantum mechanics works.
Okay. Thank you.
Well, thank you, Professor Deshmukh. I'm really delighted to attend and listen to your talk. But I have a comment and also a question for which you have already answered indirectly for my question, but still I will share with you. The relevance for the students and teachers who are assembled here about this talk, particularly with reference to new education policy in India, about which this program, entire program is dedicated. And that is, Professor Deshmukh, we have talked several times, recently only over telephone, and you only remember our close but very brief association with both of us.
Yes.
When I was Vice Chancellor. That I will not going to speak much, but how it is relevant to new education policy is something that is relevant to entire audience. You started beautifully with your talk today by referring to Krishna and Arjuna as a teacher and student.
Yes.
New education policy emphasizes that the teachers also should become mentor and students mentees. That is the relevance here. And mentor and mentee, that is student, teacher and students, are going to be playing very important role according to the new education policy. And every teacher has to become a mentor. What is that mentor and all that? You have beautifully illustrated, not only with Krishna and Arjuna, subsequently also in various names that you have brought, who are the giants of the physics. They are also very good mentees, starting from Freeman and so many other things, Feynman and others. All the names that you have cited, up to Bell's inequality, they are something very relevant to the new education policy's concept of mentor and mentee. Okay, and the kind of the various stages you underwent is really superb. I am delighted. You are a great teacher, and unknowingly you are also a great mentor. Professor Shanti will understand my comment, and she will agree, I am sure, you are also a great mentor.
Thank you very much.
I am really delighted, and we wanted to meet as early as possible. Now, I didn't have the opportunity, you also, because I was out of station most of the time. And I am sure we are going to meet shortly and discuss about your new concept.
Yes.
And my question was, what the relevance of this Nobel Prize in quantum entanglement and their experimental work and all that. But how teleportation and all the various applications in computational physics and quantum computers you are not able to bring out in detail, mostly because you also mentioned you have no sufficient time to venture into those aspects. I understood it, and therefore I withdraw my question, and this comment stands. Thank you.
Well,
Thank you, sir. Thank you.
I will take only 30 seconds to respond to your last part. You are absolutely correct, because these things are impacting our lives. It's going to make a huge difference. And for all the students, it's very important to understand teleportation, because that is how quantum computation works. It is inspired by entanglement, and that is how drug designs will be done. Okay, you cannot do it using classical computing. That is how cyber security will be enforced. That is how your money will remain safe. So it is an important part and the integral part of your life. Thank you.
Thank you very much, sir. Anyway, it is audible. Thank you very much, sir. And now I request Professor Shivaram N. Patil to present a bouquet to. Yes, sir. Yes, sir. Early, sir. Yes, sir. It is our. Yes, here I can. Hello. There is a small change in our schedule. And I request all our guests to go to the lunch. And the students, chairpersons, and the judges, I want you to be here for few announcements. Sir, others can go to the lunch. Lunch is here only. Sir. Come back at what time? Yes, you have to come back within a half an hour. ಅದನ್ನು ಅವ್ರಿಗೆ ಹೇಳ್ತೇನೆ ಸರ್. ಈಗ ನಿಮಗೆ ಟೈಮ್ ಇಲ್ಲ. That's why. Sir, there is a slight change in our schedule because it is already 2 o'clock. We cannot have right now the oral presentation. We will have the oral presentation after the lunch break. And I just want to know, OP1, OP2, yes, here. So before I tell you something, OP1 is it present? OP2, OP4, OP7, OP7, you are present. OP8, yes. OP9, yeah.